Hello, everyone. Let's begin. So before we will get into the talk itself, let's go over the structure of the topics that we are going to cover today. We are going to start by understanding what is a borrow checker, and this will be our appetizer. Next, we will have three main courses. First, we will learn how the borrow checker works in Rust. And we'll mostly focus on the NLL borrow checker because it is the implementation that Rust uses today, and also the ones that we were going to implement in C++. Then we are going to take a jump into stateful metaprogramming and learn how this obscure part of the language works. Finally, we are going to put everything together and implement a compile-time borrow checker in C++. And for dessert, we will see how we can improve this implementation with C++26 reflection. In recent years, there have been many articles calling developers to switch from unsafe languages such as C and C++ in favor of memory-safe languages such as Rust. And this is where we are going to start our investigation. So what is memory safety? When we say that a software is memory safe, we mean that it is protected against memory access-related vulnerabilities, such as buffer overflows and dangling pointers. Here we have an example of a potential buffer overflow. This code reads an index and the value, and then uses them to write the value into an element of the vector. However, if the index is outside the range of the vector, then it can potentially override other piece of memory, such as a function pointer. We can prevent this vulnerability by using a stud vector at instead of the brackets operator, which adds a bound check, and if the index is outside the range of the vector, it will throw an error. So when we end a bound check, essentially if we think we have the entire memory range of the program, and within it we have a subset range, which is the valid memory range of the vector. When we do a bound check, we check that the element that we are trying to access is within that valid range of the vector. We can also have other kind of vulnerabilities. This is invalidation, which happens when an object or a resource is modified, causing a pointer or a reference to become invalid. Can anybody tell me what is the issue in the code here? Yes?
Pushback might cause the vector to be reallocated.
Exactly. So we take the reference to the first element of the vector, and then we call pushback, which might cause the vector to reallocate and make the reference dangling. Then we think that we are printing the first element of the vector, but we might print instead other piece of memory which we do not intend to. So if you think we have the entire range of time for the program, and within that range of time we have a subset of time where the reference is valid. It starts when we take the reference to the first element, and it ends when we call pushback on the vector, which may invalidate the reference. The issue is that we are then trying to use the reference outside that valid range of time. Invalidation is not the only vulnerability that depends on when we are trying to access a resource. We can also have use after free. We might try to read uninitialized variables, or we can have a data race between multiple threads. Now, in order to prevent the buffer overflow vulnerability, we added a bounce check which checks at runtime that the index is valid. There is also static analysis, which detects issues in the code without running it, so we can catch them earlier. These two approaches of runtime analysis and static analysis complement each other, and they should be used together. So the goal of the borrow checker is to detect time of access errors, such as the invalidation example that we saw, and it does it by statically analyzing the code at compile time. So if there is an issue, the code will fail to compile. Now, this valid range of time where it is valid to access a variable is called the lifetime of the variable. And in fact, it is not a range. It is a set of points because it doesn't have to be contiguous. There can be gaps in the middle. We are going to look at more lifetimes soon. So we are going to use a special syntax to refer to the lifetime of the variable. And the special syntax is tick and then the name of the variable. So here when you see tick v, it means the lifetime of the variable v, which is the set of points within the program where it is valid to use the variable v. Okay, so first we are going to start by understanding the borrow checker in Rust. And we are going to look at some Rust code, but don't worry, I'm going to explain everything, and it is very similar to C++. So here we have a local variable called vec. The lifetime of vec starts immediately after it is constructed. And the lifetime ends when it is destroyed at the end of the scope. Now, Rust has destructive move semantics, which are like move semantics in C++, but it ends the lifetime of the variable, so we can no longer use it after it. So here, the call to drop ends the lifetime of vec, and we can no longer use it after this point. We are going to use drop as a tool to better understand lifetimes and the rules of the borrow checker. So according to the borrow checker, when we create a reference to a variable, we borrow the ability to access that variable. For how long can we access it? Until the variable is destroyed. Because when the variable is destroyed, the reference to that variable is no longer variable. So to summarize, the first rule of the borrow checker is that the variable being borrowed must outlive the reference to the variable. Let's understand this rule better with an example. So here we have a variable called vec, and I marked the lifetime of vec in green. We take a reference to vec, we borrow it, and we store it in the variable r. I marked the lifetime of r in blue. Now, according to the first rule of the borrow checker, the variable must outlive the reference. And as we said, a lifetime, you can think of them as a set of points. So if we want to formulate this rule as a constraint, we can say that the lifetime of the reference must be a subset of the lifetime of the variable. As you can see, the blue bar is a subset of the green bar, so it satisfies the constraint. But what happens if we call drop on vec in the middle of the function? Now the lifetime of vec ends when we call drop, and the lifetime of the reference continues until the end of the scope. So we no longer satisfy the constraint, and we get an error. One way to solve this issue is to move the reference into an inner scope. And now we satisfy the constraint. But Rust has a better solution because it uses non-lexical lifetimes, or in short, NLL. According to NLL, the lifetime of the reference ends at its last point of use, which in this case is immediately after the point to print, because it isn't used anymore after that point. So the lifetime of the reference is within the lifetime of the vector, we satisfy the rule, and we don't get any error. Rust also has lifetime annotations, which is a special syntax to create lifetime constraints between the arguments of the function and the return value of the function. Let's look at an example. So here in the function max, the tick a is the lifetime annotation syntax. The function takes two arguments as references and return a reference to one of the arguments. Now, at compile time, we don't know which argument we are going to return. So we need to create two constraints. One is that the return value that the first argument must outlive the return value, and also that the second argument must outlive the return value. Now, these lifetime constraints actually apply on the calling function. So here we have two variables, a and b, and we call max with a reference to a and the reference to b, and store the result in C. So it creates the constraints that the lifetime of C must be a subset of the lifetime of A, and that the lifetime of C must also be a subset of the lifetime of B. Because later, when we print C, it can either point to A or point to B. All right, now we are back to the invalidation example, but this time it is written in Rust, and we want to understand how the borrow checker prevents us from compiling this code. And in order to learn how it works, we need the second rule of the borrow checker, which states that at any point in the program, a variable can either have multiple read-only references or a single write reference, so mutable reference. You can think of it like a read-write lock, which is enforced at compile time. And this is how Rust prevents the invalidation example and also data races. So let's go back to it. And the invalidation example from the point of view of the borrow checker looks slightly different, because behind the scenes, when we call push on the vector, it creates a temporary mutable reference to the vector. Here I made it explicit and marked the lifetime of the mutable reference in orange. According to the second rule of the borrow checker, we can either have a single mutable reference or multiple read-only references at the same time. If we want to formulate this rule as a constraint, we can say that the intersection between the lifetime of the mutable reference and the lifetime of the read-only reference must be an empty set, so there is no overlap between the two. However, here you can see that there is an overlap between the read-only reference and the mutable reference, so we get an error. Here is a high-level overview of how the borrow checker works within the Rust compiler. So first, the Rust code goes through the lexer and the parser, and we get the abstract syntax tree, or AST. Now, high-level intermediate representation, or HIR, is essentially the same as AST. The first step is lowering, which converts the HIR into mid-level intermediate representation, or in short, MIR. The MIR is the input to the NLL borrow checker, which analyzes the MIR and returns an error if it finds one. Now, there is a limitation to the NLL borrow checker where it can falsely reject programs which are completely valid. And it comes from the way that it treats lifetime constraints. Or more specifically, it doesn't track from which control flow branch the constraints are created. Let's understand it better with an example. So here we have two variables, v1 and v2. And we borrow references to these variables, R1 and R2, respectively. I marked the lifetime of R1 in the green bar. Next, we have a condition where we assign R2 to R1. Because of the assignment, it creates the constraints that R2 must outlive R1. And I marked the lifetime of R2 after we apply the constraint in blue. In the else branch, we try to modify v2, which behind the scenes creates a temporary mutable reference. According to the second rule of the borrow checker, we cannot have both a read-only reference and a mutable reference to the same variable at the same time. As you can see, the lifetime of R2 overlaps with the lifetime of the mutable reference, so we get an error. Now, I know that you all want to raise your hand and tell me, but Alon, the constraint which extends the lifetime of R2 comes from the if branch, and the mutation comes from the else branch. They can never happen at the same time, so this code is completely valid. And my answer to you is yes, you are correct. However, the borrow checker is unable to see it. It don't know that the constraint comes from a different branch, so it reports an error. If you want a more practical, real-life example of code that is prevented by this limitation, and I'm sure you've seen this pattern many times before, where you have like a hash map and you want to look at some value based on a key. If you find it, you return a reference to it. Otherwise, you compute a new value, add it to the map, and return a reference. Here you can see the diamond shape of the control flow, and because of this, the borrow checker is unable to see the limitation, and it reports an error. Rust has an experimental next-generation borrow checker, which solved this issue, and it is called Polonius. Polonius can be enabled through a compiler flag, and it is named after Shakespeare's character, which said, neither a Bauer nor a lender be. It takes a different approach to the NLL Bauer checker. The way that it finds error is that it looks at all the points in the function and asks two things. The first one is which loans, or in other words, borrowed references are alive at that given point, and is any of these loans invalidated here? If it does, then we find an error. Now, these two questions might sound to you like a database join, and for a good reason, because Polonius uses datalog, which is a declarative logic programming language similar to Prolog. The inputs to datalog are called facts, and it uses logic-based rules. For example, if A and B, then C, and applies them recursively to derive new information. It adds an extra step inside of the compiler because the facts are computed from the MIR and then passed to Polonius. The facts are represented as a bunch of sets, and then they are passed to the datalog engine, which applies the logic-based rules to look for errors. So, for example, here you can see the final rule, which says that an error is found if a loan is alive at a given point, and that loan is also invalidated at that point. So why is Polonius still experimental? Why not use it today? The main reason is performance. So all the intermediate calculations that are created by the datalog engine can significantly increase the memory usage, and it is also much slower compared to the NLL Bauer checker, so it significantly increases the compile times. All right, now before we jump into stateful metaprogramming.
There's no cost, right? Is that right?
What is it?
If once it is compiled at runtime, there's no cost.
Yes, this is all compile time. There is zero runtime overhead. This is static analysis that is happen at compile time. Does anybody know where this door is from, which books or movies, and how to open it?
It's the eastern entrance of Moria, and
Yeah.
you say friend in Elvish.
Amazing, yes. It's from Lord of the Rings, and you say friend in Elvish to enter. And this is also how we are going to enter the world of stateful metaprogramming. So when you think of the friend function, with the friend keyword, we can declare or define a function that belongs in a different scope. So here we declare and define a function inside of the class A, but the function does not belong to the scope of the class. In this case, it belongs to the global scope. It becomes more interesting when the friend function is inside of the template. Now the friend function is added to the global scope only when the template is instantiated. This is called friend injection. Stateful metaprogramming contains two parts. The first one is the detector, which is a struct template that takes a template parameter called key, and it injects the declaration of a function. Keep in mind, this is only the declaration. There is no definition at this point. This function does not have a body or a return type. We use the detector to detect if the function has a definition or not. And the way to check it is to try to call the injected function inside of a requires clause. The second half of stateful metaprogramming is the injector. It takes two template parameters, the key and the value, and it injects the definition for the function, which returns the value. So once we instantiate the injector, it will inject the friend function, and then we can call it. So essentially, we have a compile time database that we can access by using friend functions. And I like to call it the friend-db. Now, this table that you see is the stateful metaprogramming cheat sheet. Be sure to memorize it, because there will be a test soon. So for each operation, we have the operation itself, we have the syntax, so how we express it in code, and we have the semantic, what it does. The first one is check, where we can check if a key value pair exists for a given key in our friend DB. Next, we have an insert, which inserts a key value pair, and it is implemented by instantiating the injector struct. And we can, after we injected the function, then we can call it to get the value that is associated with the key. All right, now it is time for the test. And by test, I mean everyone's favorite C++ game. The rules are simple. If you think that the code in the slide works, raise your hand. If you think that it does not, put your hand down. And if you're unsure, leave it somewhere in the middle. Let's start with a warm-up round. Here we insert the key 0 with the value of 42. Then we get the value which is associated with the key 0, and we assert that it is indeed 42. Does this code work? Yes, it does. Perfect. And you also get the next round for free. So if we try to insert the same key value per twice, the first one will instantiate the injector, but on the second call, because we are reusing the same template parameters, it will reuse the previous instantiation, and it will not inject any new function. All right, so now we are inserting the key 0 with the value of 42. And then we are inserting the key 0 again, but this time with the value of 43. Does this code work? No, it does not. Because the first one injects a definition, and the second call injects another definition. And we cannot have two definitions for the same function, so this code does not compile. All right, now a more tricky one. We insert a key value pair, and then we call a function which checks that the key exists. However, the check happens inside of the template parameters definition for the function. Does this code work? Yes, it does. You can use stateful metaprogramming inside of the template parameters declaration. All right, now we continue. So we call the hasKey function twice. Once before we insert the key, and we assert that it is false, and a second time after we insert the key, and we assert that it is true. Does this code work?
Maybe.
Good answer.
Yeah. No, this code does not work because the first call instantiates the definition of the template, which returns false. Then we insert the value. However, because we pass the same template parameters, it will reuse the same definition, and it will still return false.
Is that well defined? I mean, like instantiating a template after its first use, is that allowed or is it UB?
So, like, if you give a template parameter and you instantiate it, and if you provide the same template parameter, it will reuse the same instantiation. It will not.
No, that part yes, but insert after you static asserted and it already instantiated the template. Does that part is?
Yeah, this is allowed because the hasKey function does not instantiate the injected function. It only injects the declaration.
Oh, okay.
So there is no definition at this point.
Okay.
Yeah, so this is allowed. All right, so the way to solve it is to add an extra template parameter, which we are going to call eval. And we are going to give it a default value of an anonymous lambda. So when we call the hasKey, it is as if we passed an anonymous lambda to the call. And because each anonymous lambda is different, it will force the compiler to create a new instantiation for each call. And now this code compiles. All right. Now we have a similar, yes?
I just wanted to say with that eval trick with the lambda, if you were to instantiate that with the default parameter inside of a dependent context, that only works in Clang but not in GCC. If it's outside of the dependent context, then it works in both. But if it's inside, you explicitly need to pass a lambda from the dependent context through in order to force it to be a new instantiation.
Yeah, good comment. So there are some cases which I did not cover here, where if you have like nested evaluation, then you need to pass the outside eval lambda into inner ones. Good point. Here we have similar function, but instead of check, we call insert. Does this code work? So we call the function which calls the insert operation, but the insert is inside of the template parameters definition, and then we get the value. Does it work? Yes, it does. If you make changes to the friend DB inside the template parameters definition, they will be seen by the caller. However, this is not the case if you make changes inside the body of a function without an auto-return type. So here we have two functions, and in the second one we have an explicit void return type. And then we have insert inside the body of the function. Because it has an explicit void type, which is not auto or decal type auto or autoref or any other variation of auto, the caller to the function will not be able to see the inserted value, and it will not work. All right, now we are going to extend the friend DB in order to add more operations to it. And the way that we are going to extend it is that we are going to add an int version template parameter to both the detector struct and the injector struct. And we are going to define the latest version function, which takes a key and returns the highest version number that is associated with this key. The way that it works is that we start with a version number of 0, and then we check, do we have a definition for the function with the key and version 0? If we do, then we increment the version and try again. So we continue to version 1, version 3, version 2, 3, and so on. If there is no definition, it means that we went one past the highest version number, so we decrement by 1 and return. This allows us to extend the friend DB and add the following operations. So the first operation is update, which takes a key and the values, and it associates the value with the key and increments the latest version by 1. We also have getLatest, which takes a key and returns the value that is associated with that key at the latest version. And we can also get all the keys that were added, all the values that were added to the key in the order that they were added as a tuple. Now, working directly with FriendDB operations can become very tedious. So I created an abstraction to make stateful metaprogramming much more convenient. And I call it the metastate. The idea is that the metastate takes the key as a template parameter, and by default, the key has a value of an anonymous lambda. So each metastate will have its own unique key. Then, inside of the metastate, we provide a nice interface to all the FriendDB operations, and we pass the key to all of them. Using stateful metaprogramming with metastates is much more convenient, and one way we can use it is to create a changeable type. So here we create a metastate, and then which we initialize with the type of int, and then we use it to create a variable of type int. Next, we set the type of string into the metastate, and then use it to create a variable of type string. There is nothing new here. We could have done the same thing with, by working directly with the FriendDB operations, but this gives us a more expressive syntax. We can also set a bunch of values into the metastate and then get a tuple of all of them, so we can use it to store a list of values. Now, if you remember, because of the eval trick, whenever we call a function, it is as if we manually add an anonymous lambda to each call. So what if instead of writing the anonymous lambdas, we used the same value again? So here we set the values 1, 2, and 3, and each of them will create a new instantiation. Then we try to set value of 1 again, but it's the same template parameters, so it will reuse the same instantiation. This ensures that each value is added only once. So we can also use a metastate to store a set of unique values. Any questions up to this point? Okay, so now we are done with all the preparations, and it is time for the fun part of this talk. We are going to borrow Rust idea and implement a compile time borrow checker in C++. So here is once again the high-level overview of how the Rust's borrow checker works. We have the code. The code is converted into some intermediate representation. The NLL borrow checker analyzes the intermediate representation and returns an error if it finds one. And this is C++'s borrow checker. It looks very similar to Rust with a few differences. The first one, if you look at the top of the slide, you can see that I replaced the word Rust with C++. The second difference is that I added the word constexpr before of the NLL borrow checker. Because the NLL algorithm is just a bunch of functions. We are going to implement these functions in C++ with one crucial detail. Before each of these functions, we are going to write the word constexpr, and then they will just work at compile time. Shocking, I know. The tricky part is in the first step. We need a way to get the intermediate representation of the code at compile time. And for that, we are going to use stateful metaprogramming. So before we implement it in C++, let's look at how Rust does it. So the input to the borrow checker is the mid-level intermediate representation, or the MIR. Here you can see the MIR of the Fibonacci function, and it starts with a list of declarations. Now from this point on, we are not going to refer to this as declarations. We are going to call them IDs to avoid confusion. So the IDs do not use variable names, they use numbers. Here you can see an example of an ID. So for example, 0 is declared to be a mutable variable of type U32. So let's implement the IDs in C++. We are going to create a metastate which will store all the IDs, and we add a function that to add a new ID. And it takes a template parameter, the ID value as a template parameter, sets it into the metastate, and returns the latest version, so the version number that is associated with the new value that we added. So essentially, we use a metastate to map compile time values into integers. Now, there is more to the MIR outside of the IDs. But before we can implement the rest of it, there are some preliminary steps that we need to take. The first one is we need a way to represent control flow syntax. And for that, we are going to use this control flow enum, which can represent either scopes, if, else, loops, etc. We also need to represent expressions. And we are going to use this expression struct for it. So each expression will have a unique ID. It will have the return type of the expression. And this is integer because we are going to map the return type from the actual type into an integer by using the IDs. And it also takes the list of arguments that are passed to the function, along with the function name. Next, we have the instructions. What is an instruction? The instructions contains a bunch of instructions. So what is an instruction? It can either be a value of the control flow enum that we saw a couple of slides ago, or an object of the expression struct that we saw in the previous slide. So one of these two. We are going to create a metastate that will store all the instructions, and we have a function to add a new instruction to the metastate. The rest of the MIR in Rust is a list of basic blocks, where a basic block contains a list of instructions that must execute linearly without any jumps. And it ends with the successors, which are pointers to all the basic blocks that can run immediately after it. So essentially, the basic blocks create a control flow graph, or in short, CFG. Let's implement it in C++. So our basic block contains two vectors. One with the indices of the instructions that it will execute, and another with the list of the successors that can come after it. And this is the indices for them in the control flow graph. So the control flow graph is a vector of basic blocks. Now there is one more small preparation step that we need to take before we can create the CFG. So if you remember, we store all the instructions in the meta state, and we can get a tuple of all of them, but indexing into a tuple is not the most convenient. So we are going to convert the tuple into an array of variants, where each variant is either the expression struct or the control flow enum. Once we have the array of instructions, we can use it to create the control flow graph. And I implemented it by using a parser. Now, when it comes to writing parsers, I find it helpful to have all the parsing functions have either identical or similar signature. So all of the parsing functions have to be context-aware because we want to run it at compile time. And they take the list of instructions, the current parsing position, and the current basic blocks that we are parsing into. And it returns the basic block that ends the element. Let's understand it better with an example. So let's say we want to parse a for loop. So we need to split it into 5 basic blocks. The first, the initial statement of the for loop always runs before the loop itself. So it is part of the parent block, which is the blocks that come before it. Next, we have the condition of the loop, and we are going to call it the header block. And we have the statement that comes after the body of the loop, and we are going to call it the end block. We also have a block for the body itself, and the merged block. This is where the path that enters the body and the path that skips it are merged. So we need to create all the basic blocks, and then we parse the instructions into these basic blocks. After that, we need to connect the basic blocks to form the control flow graph. And on the left here, you can see a diagram that shows, oh, it's to your right, my left, a diagram that shows how these basic blocks should be connected to create the for loop. And we end the function by returning the element, the block that ends the element, which in our case is the merged block. All right, so far we made a significant progress in implementing the compile time borrow checker. We have our initial intermediate representation, which contains the IDs and the instructions, and then we can parse it into the mid-level intermediate representation, which is the control flow graph. The final step of the borrow checker will be the context-aware NLL borrow checker, but before that we need a way to get from the C++ code into the intermediate representation. And I call this step the recording. So the initial IR is stored in 2 metastates. We have the instructions and we have the IDs. And we are going to put these 2 metastates inside of a struct, which we are going to call the recorder. The idea is that we want to assign a unique recorder to a specific section of the code. So we are going to collect all the intermediate representation between the call to push and the call to pop. And at any point in between, we can get the intermediate representation that was recorded up to this point. The way that the recorder stack is implemented is by using a metastate that stores a type list. So when we call push, we create a new recorder and we push it onto this type list, which is stored in the metastate. When we call pop, we remove it from the list, remove the last one from the list. Anybody here is familiar with expression templates? Perfect. Expression template is a pattern that is commonly used in math libraries like Eigen. The idea is that we split the computation of the expression into 2 parts. First, we create an object that represents the expression, so it usually contains the functions that we want to call and the argument. And later on, we can evaluate the expression and get the result. We are going to use a similar idea. So like in the expression template, our expression class will also take the function and the arguments. But instead of storing them, it will evaluate them immediately. However, we do store the intermediate representation of the expression. So we create the the intermediate representation for the current expression. We get the current recorder from the recorder stack, and then we add the intermediate representation of that expression to the recorder. The goal of the expression class is to record intermediate representation of expressions. And it stores the result of the expression. So it essentially acts as a proxy layer. We want to make this proxy layer as transparent as possible. So for example, if we have an expression of a vector, we want to be able to use it as if it was a regular vector. And the way to achieve it is by making the expression class inherit from the base provider of the underlying type of the expression. Now, the base provider acts as a customization point, and it enables us to add behavior to the expression class based on the underlying type. So here we have an example of how to customize an expression based on its type. Let's say we want to be able to call the minus operator on an expression of type int. So we specialize the base provider for the type int, and we need to define the minus operator, which returns an expression with the name of the functions that we are calling, the function itself, so a lambda that applies minus, and the arguments, which in this case is this. In practice, most of these operations are very similar, except for the name, so I used macros to reduce the boilerplate when writing them. We also have the var class, and we use it to represent local variables within the function. So it records an intermediate representation as an expression, similar to the expression class, but it has a unique function name to indicate that this is a call to the constructor. It also has two methods, ref and mute, which create an expression with either a read-only reference, so constref, or mutable reference, so a regular reference, to the underlying variable. And I used macros to record the intermediate representation of the control flow. So here you see two blocks of code. The one on the left is regular C++ code, and the one on the right is C++ code that also records its intermediate representation. The syntax is not identical, but we are able to get very close. And with that, the difficult part is behind us, and all we have left is to implement the constexpr NLL borrow checker. So we talked a lot about lifetime constraints, and now it is time to implement them in C++. So here we have the lifetime constraints struct, which has two data members. The superset, which is the lifetime with the longer, which is the variable with the longer lifetime, and the subset, which is the variable with the shorter lifetime. So the lifetime, so the subset must be a subset of the superset, essentially. Then we have the getLifetimeConstraints function, which is a customization point that takes the information about an expression and returns a vector of all the lifetime constraints that are created by that expression. And the idea is that you can overload it to make expressions create constraints. So by default, we have a default implementation that returns an empty vector. So unless you specialize it, no constraints are going to be created. So let's look at an example of how we can add lifetime constraints. So when we use the brackets operator on a vector, we get a reference to one of its elements. So we want to make it create the constraint that the vector must outlive the reference to its element. And the way that we are going to do it is we'll override the getLifetimeConstraints function for all the calls to operator brackets on an expression, on an object of type vector. And it will return a single lifetime constraint where the superset, so the variable that lives longer, is the vector, which is the first argument, and the subset will be the return value, which is the reference to the element. And this is one way that we can add lifetime annotations to C++ types. And we can also use it to add them to built-in types and standard types because it is not inside the definition of the type. So the first thing that the borrow checker does is it loops over all the expressions in the intermediate representation and calls the getLifetimeConstraints function. If it reaches any overload that returns constraints, then it stores them in a vector. The next step is the liveness analysis, which returns a large table of booleans, where in one axis we have all the instructions of the intermediate representation, and on the other one we have all the variables. Now, and this is what we want to return. And if a variable is alive at a given point, we want to mark the location in the table for the instruction and the variable to be true. Keep in mind, at this point, we look at each variable separately. We do not use the lifetime constraints yet. All right, so how can we figure out at which point a variable is alive? Well, we know that if a variable is used at a specific point, then it has to be alive at that point. And we also know that a variable starts being alive immediately after it is created. So all we have left is to find all the points in between. The way that the liveness analysis computation works is that it starts from the uses of the variable, and then it traces backwards through the control follow graph until it reaches the point where the variable is created. And it marks the variable as alive at all the points along the way. The last piece that we need to solve the puzzle and implement liveness analysis is fixed point iteration. With fixed point iteration, we start with an initial guess of the solution for the problems that we are trying to solve. And then we have a loop, and inside the loop we try to make progress and improve our solution until it converges and no more progress can be made. When it comes to writing it in code, it usually looks like this. So we have a variable called changed, which is initialized to true, and then we have a loop over this variable. In the beginning of the loop, we set it to false, and then we run some computation. If the computation changes anything, then we set change to be true and stay inside of the loop. All right, so now we can implement the liveness analysis. And first, we compute the liveness analysis for the basic blocks. For each block, we compute two sets. The first set is called the live in set, which is all the variables that has to be alive at the beginning of the block. The second set is the live out set, which is all the variables that has to be alive at the end of the block. The way to compute the live out set is to look at all the successor blocks and take a union of all their live in sets. Because if a variable has to be alive in at least one of the successors, then it also has to be alive at the end of the current block. In order to compute the live in set of the block, we start from the live out set, and we remove all the variables which are created within that block. We run this computation in a fixed point iteration in order to propagate the information between the basic block until it converges. After we compute the liveness analysis for the basic blocks, then we need to compute the live set for each instruction. This is the large table of booleans that we saw a few slides ago. To compute it, we perform a single pass over each block. We start with the live out set, and we go over the instructions in reverse order. At each instructions, we marked all the variables which are used by the expression to be alive, and we remove the variable which is created by that expression. All right, so the next step of the borrow checker after liveness analysis is called region inference. And this is where we apply the lifetime constraints. So if you remember, each constraint has a superset and a subset, and we need to ensure that the superset outlives the subset. And the way that we implement it is by iterating over the constraints and finding a point where the subset is alive, but the superset is not. If we find such a point, then we set the superset to also be alive at the same point. Now we can have a chain of constraints, so we can say that A must outlive B and B must outlive C, for example, and or the opposite. You can formalize it however you want, but we have chains where one constraint depends on another constraint. In order to propagate the information between the constraints, we run this step in a fixed point iteration. Now, in the Rust compiler, this step is implemented in a more efficient way because it creates a graph of the constraints and then does the analysis on it, but we are not going to cover it today. Next, we have the lone, which represents a shared read-only access or a unique write access to a variable. So the lone contains the lifetime of the variable, which is an index into the Boolean table after we apply the lifetime constraints. So we can find all the points where the lone is alive. It also contains the path, which is which variable the lone originated from. And here the variable is just going to be here the path is just going to be the ID of the variable. However, inside the Rust compiler, it allows for more complex paths. For example, you can say that the reference is to a nested data member inside of the variable. But we are not going to implement it today. And we also have the access type. So whether it is a shared read-only access or a unique mutable access. The final step of the borrow checker is to look for invalid access. So if we have two loans which are alive at a given point and originated from the same variable, we check if they have conflicting access types. Now, the only valid access is shared read. So if at least one of these have mutable access, then it means that we found an error. All right, now it is time for a demo. Yes, so here we have a function similar to the invalidation examples that we saw. I added an extra if-else condition just to show that the borrow checker can handle it. So in the if branch, we call pushback, which is going to invalidate the reference. And in the else branch, we use it. And this is OK, like this is valid. However, if we try to use the pointer again, after the if-else branch, then it might be invalid because we may have went through the if branch and called pushback and invalidated it. Now this is regular C++, and here we have the same logic implemented in a C++ code that also does the borrow checking. So once again, we have the if-else branch. In the beginning of the function, we call push, which is going to record, initialize the recorder. And in the end of the function, we collect all the intermediate representation, and we validate it with the NLL borrow checker, and we static assert that the borrow checker passed the, that the borrow checker says that the code is correct. Now here we have the generated assembly for both functions, and I know that you can't look at it right now, but later on you can open the link and see that it generated the exact same assembly for both functions. So even with only O1 optimization, there is no runtime overhead. The next thing is that I have here an option to print the intermediate representations that we collected. So we have a textual definition. Let's see. What happened? Did I click something wrong? I mean, it worked.
I'm not sure. Looks like there's a compiler error. I don't know if you can see at the bottom there. What does it say?
Yeah.
Hit the see the little redo button down the bottom. Yeah.
Where?
So yeah, sorry. Coming back in the print IR.
Yeah.
And then at the middle of the bottom of the screen, next to where the output window is, at the bottom of the assembly.
Yeah.
That read the little circle
Left.
left.
Oh.
That one there. That will force it to do it, but Yeah, so it looks like, maybe have you lost web connection?
Oh, yeah, I don't have connection.
There you go.
Classic.
Sorry for the terrible
yeah.
error message for that.
Okay, so
All right, here we go.
yeah.
Drum roll.
Now for the
It is actually running now. It says compiling with a dot dot dot. That means it's
yeah,
going.
and I got green ones. Okay.
Yay!
Woo! Nice. So here we can see it prints the intermediate representation of the function. So you can see how it looks like. We have like the variables, and then we have like all the expressions. You can see that here we use the vector brackets operator, and it is also represented in the intermediate representation. Now let's say that we want to be safe and use vector at instead of the brackets operator. Then I can change it, and you will see that it is also reflected in the intermediate representation. So this is not code that I created by hand. This is actually the intermediate representation that comes directly from the code itself. Now, with the regular C++ version, if we remove it, then it will compile correctly because there is no borrow checking here. And you can see that everything compiles. Here I have the amazing conformance view. And if I try to now use the reference when it's invalid with the function that uses the borrow checker, then we get a compilation error, and it says that we failed, the borrow checker failed in the static assert. Yeah, so it works as we want it to work. All right, so let's compare the C++
Do you have to put
in
static assert there everywhere, or is there a way to automatically just have the compile fail? Is that just for demo purpose, the static assert?
No, so you would want, like the borrow checker, the way that the class works, it returns you like whether it found an error or not. And then you want to fail the compilation if the borrow checker found an error. So you need to have the result inside of a static assert. But you can also have the static assert like inside of the borrow checker class. I just have it outside so that you will be able to see it yeah, here. So let's compare the borrow checker implementation in Rust compared to C++. So when it comes to features and optimizations, Rust has more. We talked about the graph optimizations that it uses to speed up the region inference step. It also has the path, which can include data members. So Rust has more, but in C++ we have many that we haven't implemented. But so I give this point to Rust, but I haven't failed C++ here because we can still implement them. When it comes to performance, the Rust borrow checker runs as native code inside of the compiler, which is very fast. Compiled C++ is also very fast, but this is not the case for compile time code. Because running context per function, you can think of it as having a similar performance to a scripting language, and templates are even slower. So I give this point to Rust and fail C++ here. When it comes to ergonomics, Rust is designed both to be very ergonomic and around the borrow checker. While in C++ we have to use Rust and macros to record the wrappers and macros to record the intermediate representation. When it comes to choosing if we want to use the borrow checker or not, in Rust there is the unsafe keywords which we can use to opt out of the borrow checker, and in C++ we need to opt in to use it. You are open to choose which one you prefer to give this point to. And finally, when it comes to customization in Rust, the borrow checker, this is what you get and you can't change anything about it. While in C++, the implementation is just regular C++ code. You can change every single aspect of it, customize it for your own needs, maybe even have multiple implementations and choose which one to use for each case.
So what is the practical? You talked about the performance of the compiler overhead. So if I wanted to do this, and I did this in every single function that I used,
yeah.
What should I expect?
You should expect very bad performance. So do we have a borrow checker yet? Technically, the answer is yes. We can use compile time borrow checker in C++ today. In practice, the answer is no. One of the reasons is because of what you just asked. Compile times can become very slow. If you want to run a borrow checker which executes at the performance of scripting language or worse for your entire code base, it's not going to be practical. And another reason is ergonomics. So the ways that we can achieve syntax which is very close to regular C++, but it's still not. So we need to use all the wrappers and all the macros to record the intermediate representation, and doing it for an entire code base and maintaining it is not practical. So technically yes, practically no. But there are also good news, because the borrow checkers that we implemented today, we used cave tools compared to the shiny new technology that is just around the corner. And of course, I'm talking about C++26 reflection. So quick reminder of how it works. We have the double caret operator, which is the reflection operator, and it returns a stud meta info, which is a handle to the compile time information of the things that we reflected. We also have the splice operator, which is the opposite of the reflection operator. It takes a stud meta info object and injects it into the code. And there are also meta functions, which are const eval functions that run at compile time, and they operate on stud meta info objects, and we can use them to query, filter, or transform the metadata at compile time. So for example, we can reflect the information of an int, get the identifier of the type, add a pointer to it, and then inject it back to the code. And this is the reflection DB, which is like the friend DB, but it uses C++ stateful metaprogramming reflection features. The way that it works is that we declare a template struct that takes a key template parameter. And then we have the three same operations that we are familiar. In order to check if the key has an associated value, we substitute the template parameter with the key that we want to check. And then we call the isCompleteType function, which returns true only if the type has a definition. When it comes to insert, once again, we substitute to get the type after applying the key as a template parameter. And we also give the definition of the type and the definition itself to the define aggregate function, which will generate the definition for that type. And after we have the definition, then we can use it. There is another aspect of the borrow checker implementation that can be improved with reflection. So if you remember, we use the base provider as a customization point to make an expression behave like its underlying type. And the way, all the wrapping functions are quite similar, except the name of the method that we want to wrap. So I had to write them all by hand, but with C++26 reflection, we can do something better. So the functions that you see here prints the names of all the methods of a class. It does not generate the instantiation for the base provider, but it does show the mechanism that is used to implement it. So we can get all the data members of the type, check if they are a public member function, and then get the identifier and print it. There are many parts of the code that we cannot reflect with C++26, and this includes anything about the body of the function, expressions, or control flow elements. However, if we did have this functionality, then we will not need the recording step anymore. Instead, we'll be able to create the intermediate representation directly from the reflection information of the function. We do not have it today, but hopefully we will have it in a future C++ version, maybe 29.
Good luck with that.
So once again, here is an overview of the pipelines that we used to implement the borrow checker in C++. So we have the code, we create an intermediate representation of the code at compile time, we use the consexper NLL borrow checker to analyze the code, and we look for errors. wrong direction. So today we use the borrow checker to analyze the intermediate representation. And then, but in practice, we can use any static analysis method that we want. And we use the result of the borrow checker to report an error, but we are not limited to only finding errors. What I'm trying to express here is that this concept of going from code to intermediate representation and then statically analyzing it at compile time to get an error and also use it at compile to get a result and also use it at compile time is a generic pipeline, and we are not limited to using it only for the borrow checker. We can also use it for other purposes. For example, we can use it to optimize the performance of our software. So here in the code examples that you see here, we have a function that takes two allocators with different characteristics. And then we have an implementation which takes one generic allocator. What happens here is that we first extract the intermediate representation of the implementation, and then we choose which allocator we want to pass to the implementation based on its intermediate representation. There is nothing new here. This is just designed by introspection. But instead of looking at a type, we look at the intermediate representation of a function. So the way that I see it, this method of customizable compile time analysis has three general use cases. The first one is validation, where we want to validate that the code is correct statically at compile time. And it includes the borrow checker, but it's not limited to it. So for example, we might want to prevent other vulnerabilities outside of memory access ones, or we may want to validate some custom business logic. The second use case is designed by introspection, which is where we use the intermediate representation of the function to decide when or how we want to call it. And as we saw, one example is to apply optimizations to reach our performance targets, whether it is frames per second, nanoseconds, or memory usage, whichever metric you care about. The final use case is that we can use the intermediate representation of a function to generate a new function. For example, in automatic differentiation, we want to generate a new function that does the backwards pass, so it will propagate the partial derivatives to the arguments. So to summarize, we started by understanding what is the borrow checker and how it works. Now, even though when you go back and you write code, you're not going to have a borrow checker in C++. However, just by understanding the way to think about it in the point of lifetime as a set of points and constraints between the lifetimes, you get a mental tool that you can use to write safer code or evaluate the safety of a piece of code. We also talked about stateful metaprogramming, and this technique feels to me like dark magic because it is very powerful and there is not a lot of information about it. Now you know how to use this magic, and with great power comes great responsibility. We also implemented a compile time borrow checker in C++, so hopefully you get better understanding of how everything works and how to implement one. We covered stateful metaprogramming in C++26 and some of the reflection features that it adds. Overall, we covered a wide range of topics. In between all of them, I hope that you learned at least one new thing. And most importantly, I hope that you enjoyed the talk. Mitzi is a header-only library for compile time validation and analysis. It is currently in early development, so it is not intended to be used in production. My goal is to make compile time analysis into something that is both practical and accessible, but this is also a project that I'm working on in my spare time, and I enjoy working on it, so I'm going to continue with it regardless. I'm currently using C++23, and I'm planning to use C++26 for the reflection features once they will be more widely supported. So if you want to play around with stateful metaprogramming, or you want to check the borrow checker, see the full implementation, or maybe even create your own implementation, it is all available for you on GitHub. Finally, this is my cat Mitzi, and I named the library after her. Thank you. Once again, how much time do I have left?
15 minutes.
15. So I have just a bit of bonus slides. So think about questions, and then we'll get into the Q&A. So when it comes, we use static assert to find an error, but we also want to report an error message. And in static assert, we can only use a string literal, which limits the amount of information that we can provide, because we cannot take information from the compile time computation and inject it into the error message. But let's try to do it anyway. So this costume error struct is going to be the error message that we want to report, and we are going to pass it to the report error as a template parameter. Inside of the report error function, we have a static assert that always fails. And if we look at the generated error message, we can see that it does print the costume error struct as part of the template instantiation stack. However, in the error itself, it says that it failed because 1 does not equal 0. And this is not the error message that we want to provide. However, if we move the size of comparison into an inline const per variable, and then use the inline const per variable inside of the condition of the static assert, then we get the error message that says that we failed because always false of error, and that the error is our costume error struct. So we're able to print it. We can also add data members to the error struct, and they will be printed as part of the error message. So this is one way that we can add parameters. Now, the fixed string class is a wrapper around a fixed size array of characters. And because it has a const per constructor, we can use it to represent a compile time string. If we call the report error function with a fixed string, then for Clang and GCC, it will print the string as part of the error message. However, for MSVC, it will print the characters of the string as ASCII numbers. In C++26, we get user-generated error messages in static assert. So instead of a string literal, we can pass any object that has a size and data method. So we can have something like std_string with the error that we want to print, and then we can use it. Finally, you can read what's written here while I'm explaining what you are reading. So I asked in the beginning of the talk, we had a bunch of articles calling developers to move to memory-safe language. Here I asked Gemini to imagine a future article calling the developer to switch from unsafe languages to languages with customizable compile time analysis, such as C++. It gave me something like 5 pages, and then I asked it to summarize it, and now it's here on the slide. I don't know if this is actually going to happen, but I did find it enjoyable, so I included it. Thank you, and now is the time for questions.
Thank you, great talk. That was a lot of fun. So one question about like the friend name injections, like different parts I read potentially suggested that wasn't even allowed anymore by the standard, or there was something related to it. And then the second one is just, have you thought about writing a paper, call it structured lifetimes and borrowers and lenders, and then we can do this for the rest of our code along with senders and receivers and like specify everything all together?
So first question about the, is it allowed by the standard? From my understanding of it, it is not intended by the standard, so it is kind of like a loophole. However, they do not know how to remove it, because it's like the interaction between templates and friends. So it happens, and yeah, this is, do you want to add?
Well, I was just going to say, as far as I understand, because we now have an officially blessed way of doing, of checking stateful things in C++26, it's now kind of, even though there was an accidental way of checking the state of the compiler before, we now have actual ways of checking the state of the compiler. So it's, in general, I guess, valid to check the state of the compiler, even though people don't like it.
Yeah, yeah, great comment. So yeah, before C++26, it is kind of like considered a loophole or a gray area. In C++26, then we have you know, the isComplete type and define aggregate, which is a yeah, it's if you in C++26 onwards, you should be using this to do stateful metaprogramming. And the second question's about the paper. No, I did not think about it. I've never wrote a paper, so yeah. Yes.
So yeah, great talk. Thank
Thank
you
you.
for showing us the horror of stateful metaprogramming. I can never unsee this. Thank you. But what I wanted to say though, seriously, is like, imagine like forget the syntax and how you actually did it. Let's suppose C++ had borrow checking. What would change about your C++? What would there be patterns in C++ that you could no longer do because the borrow checker would stop you? Or how would your code be different?
So we would not be able to do like the invalidation things that we saw here.
Yeah.
Yeah. So, do you mean like code that is valid that I want to write and unable to write, or code that is invalid and it will detect?
Generally, how with your experience of having the borrow checker, did you find your code actually changing other than the syntax of getting the borrow checker?
Yeah, you need to structure it in a way like you have the constraints that you need to make sure that are correct. And so if you have there was actually a great talk, like I have some examples, but yesterday there was a talk by Itzhak where they implemented a borrow checker like for Google. And like like over there they said like it found like thousands of examples of code like after they added this analysis. So I mean I can give you a few examples, but taking what they had on the Google code base, I guess give a better approximation of what you can expect. And yeah, it will find like a large range of vulnerabilities which you might not notice.
Have you tried C++26 features already and measured compile time differences? Or
I have not measured the compile time differences. I haven't implemented this with the C++26 features. I will wait until I will have like where it will be more widely supported, and then I will transition to C++26 and see how much improvement I can get from it.
just so you know, it's in GCC 16.1.
Oh, yeah, good point. Yes.
So what static analysis tools external can you use that will give similar results?
I mean, you have the regular sanitizers and static analysis stuff, but in order to have the complete borrow checker, you need to have the lifetime annotations and like lifetime relationship and constraints. And maybe some tools can detect some of them like automatically, which I think this is what they did in Google. They didn't like manually write it. They tried to do as much as they can automatically.
Well, Coverity does a little bit.
Yeah, there are tools that does it. But in order to have like a complete one, you will need to have like lifetime annotations for everything. So you need a way to specify them. Yeah, as we said, like Google have their tools that does it, and I think they're about to add it to the like LLVM, and as you said, the Coverity. Yeah. Oh, how did you?
Yeah, Coverity
yeah.
does like dangling references in particular. It can detect.
Yes. So these are a couple of options. Yes.
Do you foresee being able to run your code as a tool to analyze code that may not yet have annotations and maybe add annotations and check lifetime stuff in C++?
Yeah, I mean, once you have the intermediate representation of the code, then you can run any static analysis that you want. So if you have like a static analysis way to generate the annotations from it, then you can do it. It's going to add some overhead to the compile time, but yes.
Nice talk by there. Can you give an indication how big it is, how much code you wrote?
So my implementation does not cover the entire C++ language, and it's and there are some like optimizations and features to add to it, like in order to make it more practical. The entire code is about 1,500 lines. So yeah, something around this.
Can you handle lists, for example, or is that difficult? A start list, can you handle that? Code containing more lists and iterate from lists?
It can handle this. You need to add the lifetime annotations for the type. So if you have like indexing into the list or like the iterator stuff, yeah. Yes?
One suggestion I have that might help speed up your execution, you showed the code for getting the latest version in the injection. You can actually achieve that in logarithmic time instead of linear time by doubling, iteratively doubling until you reach the end, and then kind of doing a binary search from the upper bound. So you can get a logarithmic amount of steps instead of a linear. That might help speed it up a little.
Oh, nice. Yeah, that's a good point. Yeah, I need to try it, but yeah, it can give a speed up. Okay. Thank you very much.